My name is Nikha and I work in the marketing division at Codebo. Codebo, as you may or may not know, is a pure play product engineering firm that believes in bringing ambitious ideas to life through agile methodology. And in the webinar today, we'll be talking about the transformers, the working of it, the applications, and many more things. So now, without further ado, let me introduce you to the speakers. Let's meet Vignesh. Vignesh is a senior data scientist at Codebo. He has overall 7.4 years of experience and 5 years as a data scientist. He has previous and current experience building end-to-end machine learning and deep learning applications for the power and utility industry. It's a request, so please turn off your mics, everyone. Okay. So he has a previous and current experience building end-to-end machine learning and deep learning applications for the power and utility industry, is proficient in Python and has a strong research background. Next, let's meet Sridhar. Sridhar, who is currently working as a senior data scientist at Codebo, has overall 4 years of professional experience, including around 3 years as an AI engineer, during which time he actively engaged in smart camera-based artificial intelligence application development and deploying cutting-edge deep learning-based computer vision models on various advanced AI accelerators. His master's research focused primarily on spatiotemporal data analysis and forecasting. Next, meet Amol. Amol is a senior data scientist at Codebo and has overall 7 years of experience as data scientist. He specializes in developing machine learning, deep learning, and productionizing ML models. He has worked in a variety of industries, including retail, insurance, manufacturing, biopharma, oil, and natural gas. So if you have any further questions, kindly ask them in the chat so that we can answer them in the end. So let's get started.
Okay, thank you, Nikat. So I'll start the session. So we'll start this session with the recurrent neural network. Now, what is recurrent neural network actually? So in recurrent neural network, what happens is your output does not only depend on the past input, uh, on the present input, but also depends on what was its initial output, right? And this is what the time folded version of, if I unfold this recurrent neural network, this is the unfolded version of recurrent neural network, where your next state will depend on what is the present input and what was the previous output, right? So now the recurrent neural network has actually multiple architectures. So okay, first architecture is what vector to sequence model. In vector to sequence model, what we have is like pass vector as an input to the recurrent neural network, and we will get the sequence as a output. So the example is like image captioning. So in image captioning, we are passing that as a image vector here, and we will get the caption related with that image, which is dog in a cup. Now, the second variant is sequence to so basically second variant is what sequence to vector model actually. So in sequence to vector model, what happens is the data is like given in the sequence, and basically we get the output in the form of vector. Fine. And the third variant is, so actually the third variant is, it is sequence to sequence model. So in the third variant, what we are doing is like we are giving input as a sequence and we are getting output as a sequence only. So take the example of language translation, where we are giving input as a French language and we are getting output as a English language, right? So here the words are given in a sequence and we will also get the output in the sequence. So this is sequence to sequence model, right? But there are disadvantages with respect. So basically the recurrent neural network, so whenever you have the time series data, you can use a recurrent neural network where you can use the past timestamp data. right, to predict the future. Now, there are some disadvantages related with the recurrent neural network. One disadvantage is what? It is very slow to train, right? So though we use the truncated version of back propagation, still it is slow to train. And the second one is what? So basically, it cannot support long sequence data. So basically, with long sequences leads to the vanishing and the exploding gradient problems. So then here it comes the LSTM networks. So now in LSTM network, what happens is this is the LSTM cell. So if we have to hold the long-term memory, so basically here we are giving the past input. So that past input can be passed as it is without much processing, right? So we can hold that long-term memory using the LSTM network. But again, in LSTM network, what happens is we are giving the data in a sequence only, right? And we are getting the output in the sequence. So what is happening in the LSTM network is actually we cannot use the parallel processors, right? And even LSTMs are even more slower to train than RNN. So how can we basically parallelize the uh, how can we go ahead with this parallelization of sequential data? So in 2017, actually the transformers were introduced. So Vignesh will walk you through what are the transformers and how can we use that sequential data in parallel form. Vignesh, can you please?
Yeah. Hey everyone. So Vignesh here. So as Amol mentioned earlier, there have been quite a lot of models like LSTM and RNN, and these models have been using the sequence approach and the attention mechanism, which were probably the state of the art approach that time. But then to simply put, these models are good when it comes to predicting the next word, but they're not good at predicting a complete sentence. So that's the situation where we think that transformers would be the most important algorithm. And so over here, if you notice, on a simpler approach, we can see on the left-hand side, we have an encoder and a decoder. Transformer is nothing but, imagine that you have a sentence, Jesus student is there, and you want to convert it to an English word. So whether it be English to French or French to English, or let it be any classification task, transformer contains an encoder and a decoder. What essentially it does is the encoder contains information that takes the data, which is basically human sentence, and then it converts it into a numbers. And these numbers are then taken by the decoder, and the decoder basically decrypts it back into a sentence again. And the so essentially it can be used for any kind of NLP task. NLP is natural language processing for people who are aware of it. And also it is used for translation, classification, and many other sequential approaches. And you can also think of it this way that see this encoder, there is a so this encoder and decoder approach are also there in other type of model like BERT and GPT and GPT-3 and so on. But then the approaches vary a little bit. So there are three different ways in which you can categorize them. Either it's an encoder based model or decoder based model, or encoder decoder based model. And for transformers, we basically use an encoder decoder based model. To get into it, let's go to the next slide. Yeah. So as Amol already mentioned, RNN, as Amol already mentioned, RNN scripts, what they usually do is they take the sequence of factors, and they try to convert them into a numerical representation. But then the difference is that they do it one by one. So as the word says here, right, the red dog. So if we are providing a red dog a sentence, so what basically the RNN does is it takes the red first, the first, and then it converts it to a vector representation. It then takes the red, and then it does a vector representation of it, and then the dog separately. While the transformer, what it does is, because there are multiple stages within a transformer, it it has the ability to basically run the whole sentence at a time. And you can also think, or in other words to say, uh, these models, there are Okay, I think we can explain that in the next slide. Once again, go to the next slide. Yeah. So yeah, this slide is going to probably explain them in a much clearer way. So as you see here, we have an embedding space and we have the inputs. And imagine that you're doing a specific task. Initially, any type of model that you want to build, you won't have any kind of training data necessary for it. So what in this situation, what we do is we use something called a transfer. We do something called a transfer learning. And over here, as you see on the right hand side, there is something called an embedding space. So this is something what Google and other companies have built by pre-training this model earlier only. And this embedding space essentially gives an understanding of each of these words and the relationship of that word with respect to other words. And for our model, imagine that we are going to use this embedding space for our model. Can you go to the next slide? Yeah. So imagine we have two sentences here. AJ's dog is a cutie. AJ looks like a dog. So if we have these two sentences, if you're providing it to an LSTM or an RNN, what happens is it takes the AJ first, it takes the hyphen S second, it takes the dog, it takes S, it takes A, it takes QT. All of them, it basically takes it separately. While when it comes to a transformer, it takes all of them together. But then the important part here is also that it takes the reference of each of these and the positions of each of these beforehand, and that's the difference which transformers have with respect to the other models. Where here you just don't just create a vector representation, but you also make sure that there is a positional input to it. So what I mean to say by that is, if I'm saying AJ dog is a cutie, so we are saying that we are focusing on the dog and we are saying that the dog is a cutie. While the second statement, AJ looks like a dog, we are basically saying that AJ is a dog. AJ looks like basically a dog, right? So in these two situations, the dog are at different positions. So it is very important to make sure that the model understands that the dog said in the first statement is not the same as the dog said in the second statement. Both of them have a very different context. And yeah, you can go to the next slide. So yeah, so as said, you don't have to worry about the formula for the time. So you can just remember that in this situation, you have the dog in the question 2, and there's a dog in the question 5. Can you go to the next slide? Yeah. So any kind of data that we have, right? Probably you might have to imagine this, but any kind of data that we have. So the same sentence that we had seen earlier. Imagine that, so AJ's dog is a cutie. So let's take the first sentence. And this dog is basically the second word, right? So there's a second word. Imagine AJ's dog is sentence. So all of these words, how we process this data into a transformer is, initially we provide something called a token to them. So AJ's dog is a cutie. All these words split it separately, and then you provide a token to them saying uh, the first time is AJ, AJ is 1, dog is 2, is cutie. So 3, 4, 5. So there are 5 words basically. All of them will be separated into 5 different tokens. After that, what you do is you have an embedding layer within these transformers. And as I said earlier, because they are pre-trained on basically the entire library. So when Google trained it, when they created the embedding layer, they trained it more than 300 billion data parameters were used to basically train that, create that embedding layer. So using that embedding layer, we'll be able to create a vector space for that. And that vector space representation is more like this: 0.37, 0.99, 0.01, and 0.08. So imagine that that is the initial embedding layer. What you do along with that is you provided it a positional encoding. So in the first sentence, if you remember, the dog was in the second place. So the second place dog has a positional encoding, and the second sentence had the dog in the fifth place. So the fifth place dog has a separate encoding for it. They both don't have the same encoding because they come at different positions in the word. So now when you apply the position encoding to it, you basically apply so as you can see the first formula, you are you're using the 2 I's, which essentially means that it takes the event representations of the word. In the sense, AJ's dog is a cutie. So dog is the second word, is so is the third, is the fourth word. So basically this sign position to the dimension is basically used for the second and fourth, while the cos representation is used for the odd numbers. And these two, what the position and the dimension, D model is nothing but the dimension. So it says that at what dimension and at what position basically these words are. And sine and cos, the reason why we are using it essentially because at the end it provides us a linear outcome, and that's one of the reasons why we're using sine and cos for those. And once you add the position encoding to the input embedding layer, we get an encoded layer for the dog. So which is represented as 0.42, 0.84, 0.12, 0.81, and so on. So can you go to the next slide? Yeah. So as we saw in the first image on the right side, we saw the complete structure, right? And this is the transformer component, and this is the encoder block. Can you go back so that they'll be able to relate it to that? Yeah. So as you saw here in the model architecture, we are currently seeing the left-hand side of it, where this is essentially going to contain the encoder block. This is essentially going to contain the input block, and on the other end you have the decoder block. So yeah, so let me get back to the encoder block. So as you saw in the earlier slide, we provide the positional encoding word embeddings, right? So these are the inputs basically. These inputs get into the encoder block. So encoder block, you can imagine it this way: there are two parts in an encoder block. One is multi-head attention, and another is a feed-forward network. So currently, you can just not think about add and not, because I'll explain that later. What a multi-head, so I'll go to the feed-forward, and then I'll come back to the multi-head attention. What a feed-forward essentially does is it's a set of, imagine that it's a set of deep neural network where you have multiple layers of neural networks and hidden states. So this network basically, it helps in providing the next word. So if you have a sentence like, so we can get back to the same sentence. AJ's dog is a cutie, right? So if we take the same sentence, so if you provide AJ's dog is, so it'll be able to say a cutie, or AJ's dog is a cutie. So kind of like that, or AJ dash is a cutie. So it'll be able to figure out that it's a dog. So what a feed forward does is essentially providing us the word that needs to be there, or in the sense, it will be able to predict whatever word needs to be there. And what a multi-head attention in the encoder block does is it helps in figuring out the pattern of the data, in the sense that it helps in understanding the positions of the data, and there are multiple steps that happen within it, which gives the data a representation or an attention, focus on attention. So as the name suggests, whichever words need more attention, those words will be highlighted in the multi-head attention. And the reason why it's called multi-head attention is because we don't have just one attention, we have multiple attention. So as I mentioned earlier, encoder block is something which takes the, just reiterating that, encoder block is something which takes the regular human sentence, and then it converts it to a numerical representation for the computer to understand. So in this situation, we don't have just one. So if based on the research paper that Google published, we don't have one encoder block. Rather, similar to this encoder block, we have 6 encoder blocks basically. And each of them are stacked on top of each other, in the sense that there is a first encoder block which is connected to the positional encoding, which is the actual data. And the second encoder block, third encoder block, and so on are connected right on top of each encoder blocks. So that's how they are basically stacked up. Similarly, it's the same for the decoder, but let's get back to the encoder. So within each of these encoders, there are multi-head attentions, and they are around eight headed attentions, multi-head attentions within each of these encoder blocks. So, so I'll be explaining the multi-head attention on the right side of this page. So if you see multi-head attention, when it comes to a transformer, unlike RNN or the other methods, in a transformer, what we do is we basically split the same positional encoding word embedding into, yeah. So we split the initial data into 3 different parts. So one is the key, the query, and the value. You can imagine it this way. So for an easy understanding, query is nothing but, imagine that you are querying something on YouTube, in the sense maybe you're looking for MKBHD, or maybe it's some other channel, right? Cooking or whatever channel that you're looking for. So you type the query there in the search box, and once search, you immediately get the keys, which is the headings of each of these videos. The content is basically the values of it. So imagine that you can split them that way. So that's the same process that we perform in a transformer too. So you have a key, you have a value, and you have a this thing. So basically all three of them, a query you have, all three of them you have. These three inputs are basically nothing but the position encoding input that we have. These three inputs, where initially what you try to do is you multiply the key and the query, which is nothing but the matrix multiplication you're doing, and then you basically scale it. So in this situation, the reason why we do matrix multiplication and scaling is because we want to understand what is the score that these two keys have, right? You can go to the next slide. I'll come back to the slide again. So for better explanation, Amal, can you go to the next slide? Hello.
Vignesh, you can
Yeah.
probably share your screen. I guess Amol has got disconnected.
Okay. Just give me a moment. Yeah. Okay, is my screen visible?
Yeah, thanks.
No problem. Yeah. So if you see this, yeah. So if you see this transformer layer, yeah, let me get back to this. Yeah. So over here, right, we have the inputs. So when I spoke about the key and the query and the key, initially what we do is we do a matrix multiplication of that. And the query and the key is nothing but the same words that we use. So like I said, the AJ's dog is a query. So similarly, imagine that you have a sentence like the big red dog, and the big red dog. So this is the query side, this is the key side. And when you matrix multiply them, you'll be getting a set of values for it. And in these values, as you can see, there is a score that it provides to some of those. So whatever it finds them, so this is basically the values that are common between both of them. So naturally they'll be high. But apart from that, there are also certain words that it feels that has a very different representation on two different words. And that's the reason why it has basically marked them, highlighted them, and it's also a common word, right? So it has highlighted them with a different attention score. So this is what we basically do it over here. So when you are matrix multiplying, you basically try to identify what is the score for each of those values when you're multiplying the query and key. And then we try to scale it. So for any kind of neural network model, it's important that we need to scale the data, because if the data is of actual inputs, right? So there is a chance that the model might be taking quite a long time to basically understand it, because they are all of different sizes. Maybe some values are 100, some values are 10, and so on. So it's important that we scale it. And with respect to the research paper that Google published, what they did is they basically divided these values, they basically divided these values by square root of d. So that was the formula that they used. And once they did the scaling, masking is optional in this situation for an encoding layer. Then what we do is basically doing the softmax. So softmax is basically used for uh, aggregate. So creating a probability score. So you are creating a probability between 0 to 1, basically. Any of these scores that you see up, any of the scores that you see here, these are basically scaled. So you can say that the values which are of low importance are the values which are 0.09, 0.05, and so on. And the values which are close to 0.8, 0.71 are the values which are actually scaled to a higher value. So this is usually what happens with the softmax. It scales them in order to make sure that the higher values are given a higher score, and the lower values have a lower score. So once the softmax is done, the values that we have initially created, right? The values that are done with the position encoding, these values are again multiplied with the softmax outcome. So what essentially happens is any value, as it mentions here, any value that is going to be represented that has a different meaning in different sentences seems to be highlighted at this stage, basically. So which is what happens in this area. And these are the steps that usually happens in a multi-head attention. Also, after this, what happens is, so this is one attention, right? This is single dot product attention that we have created. But similar to this one attention, there are also different attention layers that we create. So as I mentioned earlier, there'll be eight multi-head attention layers created. And each of these multi-head attention layers will be concatenated all together, and then they'll be multiplied by weights. So if someone who understands, who has a good knowledge on deep learning, will know that each of these layers, so for them, an explanation for them is each of these key value and the key query and the value, all of them will be having its own weight vectors, and you'll be multiplying the weight vectors along with those. So you'll be having in your, imagine that you have an input embedding data. All of that will be multiplied with the uh, query weight, key weight, and vector value weight. All of those weights will be multiplied with those to create a key query and query key and value. And then these processes happen, and then all the heads, different head attention, all of them are concatenated all together, and then they are multiplied with another weight vector to create a linear layer. So this is the place where we actually have the feed forward network, which essentially takes the output that comes out of the first multi-attention layer. This feed forward takes the output of it. It flattens the layer in order to make sure that all the values are there simultaneously, and then it runs through the same process that we usually know, right? And add and norm is nothing but the reason why we have created add and norm in between is because this is the layer where you take the output of the multi-head attention, and we also add the inputs, the inputs that we have, right? So we'll add both of them, and then we'll create a layer. This is in order to make sure that the data, so there is no kind of so when we do batch processing and stuff, we basically do to make sure that the data is normalized completely. And when it goes to the next layer, it doesn't overfit, and it doesn't. So it is basically to make sure that the data is good. So the add and norm layer acts the same way on both the ends. And as I said, the first encoder block layer is also connected to other encoder blocks. So the output of this encoder block will be uh, a, a key data again, key and query data again, which will essentially be going there. And then these same process keep repeating up to the end. So yeah, so this is what you see over here. You basically have the embedding layer, and then you have the position encoding. All of them go to the multi-attention, and then the normalization happens with the attention layer. Then it goes to the feed forward where you have the neural networks, which will try to predict the next values, and then it will have all those values listed out here. So the same inputs that you have here will be here, but then it'll just be it'll be after this encoder block is performed its tuning. So we know that we'll be having 512 layers or 64 layers or so on, right? So each of those encoder block layers. So this is what happens within them. And then what happens? So now we are going to the decoder block. So the encoder block essentially does all the different encoding layers. The same process happens again and again and again. And at the end, you have the key and query coming out of this. On a decoder block, what we do is, as we are in the process of machine translation, we'll be having the output shifted writer. So we'll be having basically the French words or the English words, whichever words that we want to translate it to. So in this situation, the big red dog is there. So the big red dog is basically converted into French words. So the French words are provided in the same way. The output embedding happens the same way as it happened in the input layer, and the position encoding happens the same way as it happened in input layer, in the encoding layer. There's not much difference in this approach, but the only difference that we have with respect to decoder layer is the masked multi-attention layer. So what we do here is that All these processes remain the same, but the masked multi-head layer, it does the encoding, and it does it. So in this layer, whatever French output that we are getting in, right? It is when we do the key and query multiplication, as we did over here, as we do the key and query multiplication uh, in the decoder block, we also make sure that we mask the future outputs. So getting back to this diagram on the decoder side, imagine that these are the French words now. We have the French words here. So the words that are in the past have a value. These words have a value, but then these words are set to infinity. The reason is because we basically want to make sure that the future words are not already known by the decoder block. Rather, it has an understanding of the past words, and then it's able to also predict the future words for it. So that is one of the reasons why over here in the masked multi-head attention, we don't have future words. And this one in this layer, similar to how we did in the encoder block. Once we do this, the masking happens over here. So we are using the optional mask that we don't use in encoder block. We'll be using it in a decoder block where the future words are masked, and then it goes to the same softmax process, and the values get multiplied to it. So essentially, to show you, yeah, to show you, it'll be so these values will be there. These values are not given. These values have to be figured out, and when it goes to the softmax function, and then when it multiplies with the actual values, it will basically be able to figure out this embedding score for it. So that is when it will be able to figure out that the first word is 1 and 000 and 0.9 and so on. So if you compare the encoder decoder layer together, what we'll try to see is that the input, which is 0.71, 0.04, 0.07, 0.18, and so on. So the highest value here represents the second highest value here. So this one, big, right? So big is represented over here, so 0.13 maybe. And then red is represented as 0.62. Dog is represented with 0.91. So similarly, there'll be values which will be representing these values, these same values, but on the decoder side. And this how it matches the word to word, and it's able to give out the right representation of the French words for the English words that we are providing at the input layer. So this part that we're talking about goes through here also. So the first layer does the translation. The multi-head attention does the initial comparison, and it tries to identify the keywords that are in the French words that are as important as the words in the English translation too. So it will mark all those, and then it will send it to the multi-head attention, where from the encoder layer we have connected it to the multi-head attention over here, and this one, and from the decoder layer also we are connecting the values. So these take the same steps as we did earlier, and we'll be multiplying the key and value from the encoder, key and query from the encoder, and the value from the decoder layer, and we'll be repeating the same process. So at the end, all of them go to the feed forward network, and it will be able to give us the probability output similar to what we did earlier, where it will say that for the first word lay is given. For the second word will be given. So gross, share, row. So all those individual words will be provided for the individual inputs that we provided earlier in English. So all of them will be linearly provided one-to-one, as we are providing a linear neural network layer at the end. So this is a complete representation of the whole thing. Also, one more thing to inform, one more thing to update is that each of these inputs that you're seeing, all of them happen in a parallel way, in the sense that all inputs, so the big red dog, all those words go to the model at the same time. They don't go at different times, like the doesn't go first, big second, red dog four. It goes, all of them goes at the same time, and they happen in parallel. So all these processes that you see, all of them happen simultaneously, and that's the reason why self-attention model is much better than any other approach that is earlier done, because it's able to figure out not just the representation of each of them, but also the internal meaning of each of them. So yeah, so this is about the transformer components. with respect to applications, I believe Sridhar will be able to take it next.
Yeah. Thank you, Vignesh. Yeah, hello everyone. Hope my voice is audible. Like if you cannot hear in between, like please let me know. I will try to repeat it. And yeah, let's just start. Okay.
You want a screen share?
It's fine, Vignesh. Yeah.
Okay.
Okay.
Yeah.
Yeah. Okay. So coming to the application side, like let me give you an overview of like some of the applications that are possible with respect to like a transformer deep learning model. Like as you all know, like transformer is a like a deep learning model that adopts mainly the self-attention mechanism, differentially like weighing the significance of like each part of the input data sequence. So like it processes each element by element, and it is used primarily like in the field of natural language processing, and recently with a far more advancement in computer vision. And like transformers are like mainly designed to like work on the sequence data. Like we'll take an input sequence and use it to generate an output sequence, and one element at a time. So like there are like different like applications like spanning across different industries. So like they use it for like different use cases, and one of the most prominent one is the machine translation part, like where they like use the language modeling technique. So here, if you see here, previously before coming to transformer, like we have like the sequential nature is available for RNNs, but like it is very difficult to fully take advantage of the RNN network, because like we have like fast computing devices like GPUs and TPUs, which excel at parallel computing, not at sequential processing. And CNNs are like much less sequential than RNNs. So hence we come to transformer for this kind of a machine translation problem. And here, like in this particular example, like we have a transformer network, like how it is working for like language translation, particularly for like English to German and vice versa, compared to the RNN and CNN like networks. And like mainly the neural networks, or like for like machine translation problem, like they typically like contain an encoder, as explained previously, like reading the input sequence and generating a representation of it, and a decoder that generates the output sequence like word by word for like while consulting the representation generated by the encoder with the help of attention. And as you can see here, like the transformer like outperforms both recurrent and convolutional neural network models on this current problem of translation. And similarly, like the paper also explained, like it works for multiple other like language data sets that was used as a benchmark, like English to French, French to English, vice versa. And on top of it, like it also like provides a very high translation quality, like the output quality, and moreover, like the transformer like requires a less computation to train, and is much better fit for modern machine learning machine translation problems. And here we have they have used like the blue, that is the accuracy metric that is basically between 0 and 1, but the graph is plotted for percentage. And like it is a metric that is mainly used like a bilingual evaluation understudy, a metric for evaluating the machine translation translated text, like how accurate it is. And like as you can see, like the main use case, like it can be used it is already being used for like so many like language translation applications across like different platforms like web, PC, mobile, etc., and for across different mediums as well, like voice to text, text to voice translation. It can be used. Yeah. Next slide, please.
Yeah.
Okay. And yeah, that is all about machine translation. And here, coming here, okay, we have like a document or text summarization. And like here on the left side, like you can see. So like to brief about like why we need this kind of a problem, like every day, like the amount of text available online is increasing at a very fast pace. There are like fake news and like fake tests, that is a different part, but like the amount of text, hence like text summarization has become a very essential problem in the research side and also in the application side. Most of the modern text classification systems, like recommender systems, like they require like going through huge amount of data for showing it to the end user, and like generating like precise and fluent like summaries is a very time consuming task. Hence, like we need to it is very important to come up with some technique to make this process more time efficient, and that is the main objective of like text summarization or document summarization, like extraction of useful information out of a huge amount of text, and reduction in the reading time, and enable to read more articles like as the time for reading each article increases like rapidly. Hence, it is very important to gather information and then summarize it without like losing much time. And like this will also like enable like users to like select like multiple articles in a short span of time, and because like most significant aspects of the contents are captured. And here for this there are like a lot of examples. Like one of the recent research work like involves developing BART. It is different from BERT, but it is like a little enhanced version of BERT. They make slight modifications at the activation function part and like the GPT part, and it is like named as bidirectional auto regression model, and it is the same like sequence to sequence model for natural language translation, and it is mainly used for like text generation and like comprehension analysis, and so many like similar problems. And main use case, as I mentioned, like summarizing the news articles, like that is one of the prominent problems with respect to this application. And coming to the right hand side, like question answering, and here also like this is one of the like important application. Like you have like so much structured data, and like you need to like there like given a question, like you need to like give a constructive answer. So the question answering, like basically it comes under two sections, like extractive and abstractive. So like you have like a huge context, and extracting the answer from a given context is one method. Extracting extractive question answering. Next one is like abstractive. Abstractive is like generate an answer, like you like from the given context. And here in this particular example, like we have a conversation-based question answering problem, and here like one of the innovative work is like along with transformer, they have like graph attention networks that is mainly like an underlying database, like mainly used to understand the intent of a given question. So understanding the relationship between the tokens, and like formulate a query and retrieve the answer from the knowledge base. And yeah, this is, and they also like use the same technique like semantic parsing and the usual conventional question answering work. And yeah, this is also like majorly used for like AI based chatbots, like recently across web and Android applications. Like we have like automated chatbots like that gives technical support. That is also like one of the prominent example for question answering. Yes, next slide please. Yeah. Okay, and there are two more other like important domains that we would like to describe here. Is like the gene sequence analysis. So okay, gene is like a very important unit, and like it's very it's responsible for storing like a genetic information in all living organisms, and like their expression will give you will determine the functionality of a cell. So therefore, like any kind of like a gene mutation, like single, multiple mutation, like they can in a gene expression can lead to dysregulation, and like this is only like termed as a like a genetic disorder problems, and like a lot of problems in like medical domain, like cancer is a type of a genetic disorder when it comes like because of some mutation in like some part of a gene called like oncogene or something like that. So so mainly in this domain, like currently there are like a lot of research activities that are coming up to like accurately predict this kind of like subtypes in the gene expressions, and like estimate like whether the gene sequences have any disorder, and and transformer is like particularly the BERT based model are like very predominantly used. And here for this particular example, like we have used like a BERT promoter that is like one of the like novel research work that is recently done. like predicting the DNA strength from a given sequence. So given a DNA sequence as an input to the model, like it will predict the strength of the DNA sequence and like mainly like extract the features out of it, and that is one of the novel work. And yeah, that is like one part. Like it can be used for like variety of other problems as well in the medical domain, like for disease classification in medical imaging and computational biology. Like so many other research domains are available for which like transformer is used. And coming to the right side, like video instance segmentation. So currently, like with the advancement of vision transformer, particularly vision transformer, like transformer is as a deep learning model is mainly applied to image-based data. So mainly for some of the computer vision based problems. Like one of the major problems is like the end-to-end multi-object tracking. So like multi-object tracking or like a person re-identification. Like imagine like the person is coming in a camera, like there are multiple people and you want to track a particular person like across like multiple frames. Like person can overlap, but at the same time you need to like accurately track a person. Currently like transformer is coming up with uh, like various like techniques, like particularly segmenting like objects across each images. And one of the recent work is like the video instance transformer that segments instance in each frames. And like one major difference between like the transformer and like CNN is like CNN will have uses like pixel arrays, whereas visual transformer like splits the images into visual tokens. So like that is one of the major difference, and they are widely used for currently also like for image classification and object detection and problems. Yeah, that is from this slide, and if you can go to the next one, please. Yep. And coming to the summary part, just to summarize, like comparison between like transformers and the early version of sequential learning models, like RNNs and different versions of it, like previously explained, to give the reason for like rise of transformers, like how it is better from the previous models, and for like how it can be suitable. Second one, like the working of the transformer with the like detailed explanation about the architecture and the attention mechanism that is present in it, and its importance for the sequential data problem. That is also explained by Vignesh. And third one, the major applications of transformer deep learning model and the use cases. Like we have just covered like 5 domains, with some latest research works that is applicable to those domains. There are other latest work are also being done in those domains, and other potential application and research areas include speech recognition, image retrieval, person re-identification, and pedestrian trajectory prediction. Those are mostly computer vision problems, and vision transformers for classification and object detection, and drug discovery serious problem for medical domain, and SMS or online spam detection, and one of the most important one is the fake news identification that is recently popular among the research community. Yeah. Yes, yeah. So yeah, that's it from our side. Any questions or queries, you're most welcome. Thank you.
Before we move to Q&A, I would like you to fill the feedback form. I am putting that link in the chat box, so you guys can fill the feedback form till then. Yeah. There are some questions in the chat box. Amol, Sridhar, and Vignesh, let's just address them side by side. Should we use CNN along with RNN for image captioning?
Yeah. So I'll be answering this. Yeah. So we can actually do that combination, but it is more than image captioning. I would say it would be more applicable with respect to frames of a video, right? So where you also want to identify the person. but at the same time, you also want at a different time step. So if there's a change in movement, so in those situations, I think CNN and RN would be more applicable. But then for image captioning, I would rather go directly with CNN unless the CNN RN combination is actually giving any kind of improvement with respect to that.
Another question is, what is the name of this pre-trained word embedding by Google?
So actually, I mean, this is part of a process in the sense that there is an embedding layer that you essentially created. So as I mentioned earlier, initially you have the tokens which give you the timeline of it, where the embedding layer you have a function within the package which you can use it to to make these. I mean, to create these embedding layers for each of these words. So we just saw 4 words, but then imagine that you have in a real situation, it will be probably like you mentioned, Sridhar mentioned, it will be like a text summarization or something, right? Where imagine you have like a 4 paragraph or 5 paragraphs of information, and you will want to summarize that to a shortened version. Then you should be able to read all those words simultaneously and then provide an embedding layer for those. So as Google has already pre-trained them, there is no specific name for it, but it's just a function that you'll be able to get it out of the transformer block, and you can use it to provide an embedding information for each of the words that you're providing based on the positions of it. So that is how it can be done there.
So the next
And there are a
question,
bunch of
yeah.
claim to use. Yeah, so there are a bunch of research papers that claim to use transformer for image segmentation. Does it give any specific advantage of state-of-the-art models like UNet? Um,
Okay,
so, yeah,
Videsh, go ahead.
yeah, you can go ahead. Yeah, not a problem.
Okay, I can take this question. So basically, in unit, what happens is like we are using convolution neural network. Because of the convolution, again, there is a problem of long ranges, right? So it's all about the context, right? So here in unit, we have the localized context more, and in transformers, like we have global context. So basically, we can combine this unit and transformer together. So basically, there are a lot of papers. The combinations of unit and transformers work better than independent unit and independent transformers.
So there's one more question. How is the performance of transformer and language translation as compared to LSTMs? Do you want to take it, or shall I take it?
You can take it with next hour.
Yeah. Yeah, so LSTM, as you mentioned, right? LSTM, what it can do is, so there is a lot of difference in performance in the sense that, like you mentioned, the transformers, the LSTMs don't have a global context of it. Rather, it is creating a contextual layers based on the hidden layers that you have inside a neural network. So yeah, so as you know, LSTM is the next stage for an RNN, right? Where in RNN, if you have one word, you have a memory state in LSTM where you can take in more data, but there is only a certain level of data that you can basically use in an LSTM, and you can create a context for that. But when it comes to a transformer, it has a global context, and it understands the positions of the input vector and the positions of the output vector, and it is able to basically create a translation mode for it. So there is a much better understanding and more accurate. And it's also simultaneously more accurate in terms of providing very accurate solution. So the two examples that we used there, right? The dog situation. So imagine that that sentence was much bigger and the context was very different. So it won't be able to, an LSTM won't be able to capture all the information together, but a transformer will be able to understand everything because it has a self-attention layer in between. Can you explain the implementation details of document summarization case study? Okay, so I think that probably you might have to look at it. I can provide you the link to it. I think it will be easy that way. But maybe I can take the next question.
Right, because it will take a lot of time to explain
Yeah.
everything, documents.
Yeah, we can just share the link at least, like to.
Yeah,
Yes, we can.
we'll add the link over there. Yeah. So there's no certificate. How we have to show.
It's all about certificates. So
Okay.
Khushbu can actually answer those.
Yeah, I guess that's all. Yeah.
So I guess that's the end of the question and answers. So that's all what we have got you for today. Thank you for joining us for today's
Nikhat,
webinar.
just a second. So, guys, just want to say that we have various openings in Corpo. So, if anyone would like to, have a look at the opportunities, I am sharing one link with you, which you can use to, explore all the job openings at Corpo. Yeah,
Yeah.
Nikhat, go ahead.
Yeah. So thank you, everyone. That's all we have got for you today. And thank you for joining us the webinar for the Transformers today. We appreciate that you participated in the webinar, and I hope we were able to deliver the webinar with much ease and answers you all the queries that you have in your mind. So if you have any further queries or if you like any further information regarding Transformers, please feel free to contact us. Till then, adios. We'll see you soon.
Thank you.
Okay, thank you,
Thank
everyone.
you, everyone.
Thank you, everyone.
Thank you,
Thank you, everyone.
everyone.